Hi, today we're going to take a look at quadratic surfaces, and we're going to be dealing a lot with these. Now remember, these are basically quadratics like circles, hyperbolas, ellipses, all those other ones that are parabolas. And we're going to talk about them as a three-dimensional surface, so we're going to be adding another dimension to them. So in order to do this, we're going to start taking a look at just what their equations are. So we have like 1, 2, 3, 4, 5, 6, 7 major of them, okay? And for the most part, they're pretty easy to do. For example, we have what's called an ellipsoid. Now, an ellipsoid is a shape, and if you look down here, it kind of looks like a football, but it's like a circle that's been kind of flat, like a sphere. That's kind of been flat. Matter of fact, all those shapes are going to be down here below in the notes, which are attached to my unit on this one. So the first one we're going to take a look at is an ellipsoid. And if you notice, it almost looks like the equation of a circle. Like if I had a circle, x squared plus y squared equals r squared. But now I'm adding this z squared right there. And we're dividing by this a, b, and c. Matter of fact, so this is called an ellipsoid. Now, if a, b, and c were all equal to each other, like if a equaled b equaled c, then this would be a sphere. So kind of like when you did ellipses back in the early days of pre-cal, like if you had a squared and b squared, that would be an ellipse. But if a and b were the same number, we would get a circle. Likewise, in an ellipsoid, a, b, and c, if they're different, we have an ellipsoid, but if they're all the same, we get a circle. So if we say if a is not equal to b, not equal to c, that's how we get our ellipsoid right there. And we're going to talk later on about actually how to graph these. Next, we have a cone. Now we all know what a cone looks like. Ready? They look kind of like this, right? We have a cone, and this is a cone that its opening is going to be parallel to the xy plane. So for example, like if here's my cone, there's my y-axis, and there's my x-axis, this opening is going to be parallel to the xy plane. Right there. We can tell because the x and y go first. Now, it's going to open up on the z-axis. So that's where this opens up at. This is going to open on opens on the z-axis. Now, sometimes we say it corresponds to the z-axis instead. So, and all that really means right here is that, and we can tell because we look at the minus sign right there. I always say look for the odd man out. And all of these, if you want to know which one it opens or corresponds to, look for the odd one out. This is a minus right there. Next, we have what's called a hyperboloid of one sheet. Now, again, this is going to be on the xy. This is going to be on the xy plane, but it's going to correspond to the. If I look here, it's going to correspond again to the z-axis. Right here. Now, if we look here, let's say I get rid of this x and z right here. Well, what shape is that? Well, that's going to be an ellipse right here. So what this is saying is on the xy axis, if we let z be 0, on the xy axis, we get an ellipse. On the xy plane there. So if I think about that, here's the x and here's the y. What's going to happen is I'm going to get an ellipse on this. Right there in the xy plane. Whoops, let me get rid of this. And on the z-axis, so if I let x be 0, if we let x be 0, notice we get y minus z. Well, that's the equation of a hyperbola. Same thing here on the xz. It's still going to be x minus z squared, and that's another hyperbola. So that says if we're going up, this forms a hyperbola, kind of like this. Whoops, missed it. A hyperbola on both sides. We're going to talk more about how to graph these later on. And we get what's called, and if we combine those, because remember it's spinning around, we get a hyperbola. So this is called a hyperboloid of one sheet. Right there. Notice the differences between the cone and the hyperboloid. And the cone will equal to 0, and the hyperboloid will equal to 1. Looking at the elliptical paraboloid, this is called an elliptical paraboloid, and we can kind of tell right here, and one thing I want you guys to tell here, this is called an elliptical paraboloid because if we look right here, we get an ellipse. Again, on the xy plane. So if I were to graph this on the xy plane, again, I would get an ellipse. The z here equal to z, single variable, says this is going to correspond to the z-axis. Remember that corresponds, which means it opens on the z. And what happens is, well, I kind of messed this one up. If I let x and y be 0, I just get a point here, so I should have mentioned that real quickly. So this is going to open up like here. And what I do down here is like every one of these little shapes right here makes an ellipse right there. So if I let z, simply put, like if I let z be 0, I just get x squared equals y, so there's going to be a point there. But if I let z be 1, I would get an ellipse. Z be 2, I get an ellipse here. Z be 3, and I'm just building an ellipse right there. Next we have what's called a hyperboloid of two sheets. Now notice the difference between a hyperboloid of one sheet and a hyperboloid of two sheets. The big difference is when we it's that -1. Now sometimes what I'll do to make this one, you might see it this way if I divide through by -1. X squared over a squared minus y, I guess I should do it right. If I divide everything by -1, we would get z squared over c squared minus x squared over a squared minus y squared over b squared equal to 1. And this is typically how we tend to see it. In hyperboloid of two sheets, so it's going to be the same thing as hyperboloid of one sheet, but one sign is going to be negative, the sign is going to be negative, or two of the signs will be negative. And again, to determine how it looks, we look at that z-axis. So this again, it corresponds to the z-axis, which means it's going to open up on the z-axis right there. So how does it look? Well, it's going to look the same as the hyperboloid of one sheet, but we're going to get this negative. For example, if I let x be 0, or if I let z be 0, if you notice, we get this negative x squared minus y squared equals 1. That is not the equation of a hyperbola, because really what is that saying? I'm saying that x squared plus y squared equals a -1. And you can't have that. So what that's saying is, unlike the hyperboloid of one sheet, where I have an ellipse at the center, here instead, whoops, I guess I should draw it right. If we have our x and we have our y, instead we're going to have nothing here. So it's going to start above. And it's going to look below. Like that. So that's our hyperboloid of two sheets. And the reason and they don't connect. So there's no connection because if I let z be 0, I get x squared plus y squared equals -1, and that cannot happen right there. We're going to talk a lot about that on the next day too, okay? And then the last one is called our hyperbolic paraboloid. This is the fun one. Okay, this is sometimes called the saddle. And again, z is the odd man out, right? It's x squared, y squared, z is all by itself. So this is going to correspond, again, to the z-axis right here. And how does this look? This is our weird one. X, y, z. It opens up on the z-axis. So there's a couple ways you can do it. One, if I let z be 0, I'm going to get a point, single point there. Okay? If I let x be 0, what shape would I get? I would get a parabola right there if I let x be 0. So that's saying on the xz plane, I'm going to get, on the yz plane, I'm going to get a parabola. But be careful, which way is the parabola opening? Down on the yz plane. So I'm going to get a parabola that's kind of opening down on the YZ plane. If I let y be 0, I'm going to get a parabola. So on the XZ plane, I'm going to get a parabola that opens up. So I'm going to get a parabola that kind of goes up like this. So I draw that parabola. Now that's the one I draw first. Now, remember this is opening up on the X, and next, so basically whatever's first here, I just draw it on the X-axis. We're going to talk more about this tomorrow. On the Y, it just opens down like this. Just remember we saw that in the YZ plane, we get a bunch of parabolas opening down. And what you get is a shape that we call a saddle. We're going to be terrible at drawing these later on, I promise. And then we have the elliptical cylinder. The elliptical cylinder is if A equals B, then it's a circular cylinder. So basically, the cylinder, notice for the cylinder, one of the variables is always missing. For a cylinder, one variable is missing. That's the easiest way to determine the cylinders. For example, over here, we have an elliptical cylinder. If A and B were the same, it would be just a regular circular cylinder. Here we have what's called a parabolic cylinder. So let's see what this looks like. Y squared equals Z, right? Or basically Z equals Y squared. If I were to graph this, there's X, there's Y, of course there's Z. This is a parabola on the Y on the XZ plane. So it would open kind of like this. There would be our parabola. Well, what does a cylinder look like? It opens on the X. Now be careful. This opens on the X-axis. How do I know that? Well, the X is the one missing. X could be anything. And I just go down like this, and there is our cylinder. Of course, it goes in the other direction too. Okay? And you can kind of see like a little bowl, like a little trough, something like that. And if you want to take a look at what these all more carefully look like, there's a bunch down here. Please take a look at them. And we're going to talk in the next video about what's called a trace. I hope this makes a little bit of sense for you. We're going to spend some time on these, okay? I'll see you soon. Bye-bye.